Assalamualaikum dan selamat sejahtera. Prospect of combined cycle power plant over conventional single cycle power plant in Malaysia. In Malaysia, the rising demand for electrical energy is a notable feature. Most of this energy is needed for domestic and industrial appliance, electrical machineries and electric traction. Our country has a huge population with increasing demand for electricity. The importance of electricity in everyday life in Malaysia has reached such a stage that is required to protect the power system from harm during fault condition and to ensure maximum continuity of electricity supply. The power system of Malaysia is facing several problems which are causing deficiency of electricity generation. The problems are such as low production of electricity than the actual demand, faulty power system, lacking of natural resources required for electricity generation, and etc. This paper gives a brief description about the efficiency of combined cycle and single cycle power station and shows the comparison between them to analyze that whether combined cycle power plant are more efficient for Malaysia or not. This paper also discusses about the problems in electricity generation in Malaysia and how to mitigate the desired electricity production by solving these problems. Using combined cycle is a wise choice as the heat energy which is produced in the gas turbine is reused to boil the water into steam and supply the steam into the steam turbine to produce additional electricity. So the combined cycle power station is the better option for electricity generation in Malaysia. The main objective of this paper is to discuss the development, important challenges, progress and prospect of combined cycle power plant in Malaysia. How do gas turbine works? Gas turbines are comprised of three primary sections mounted on the same shaft: the compressor, the combustion chamber or combustor and the turbine. The compressor can be either axial flow or centrifugal flow. Axial flow compressors are more common in power generation because they have higher flow rates and efficiencies. Axial flow compressors are comprised of multiple stages of rotating and stationary blades or stators, through which air is drawn in parallel to the axis of rotation and incrementally compressed as it passes through each stage. The acceleration of the air through the rotation blades and diffusion by the stator increase the pressure and reduce the volume of the air. Although no heat is added, the compression of the air also causes the temperature to increase. The compressor air is mixed with the fuel injected through nozzles. The fuel and compressed air can be premixed or the compressed air can be introduced directly into the combustor. The fuel-air mixture ignites under constant pressure condition and the hot combustion product gases are directed through the turbine where it expands rapidly and impact rotation to the shaft. The turbine is also comprised of stages, each with a row of stationary blades or nozzle to direct the expanding gases followed by a row of moving blades. The rotation of the shaft drives the compressor to draw it and compress more air to the certain continuous combustion. The remaining shaft power is used to drive a generator which produces electricity. Approximately 55 to 65% of the power produced by the turbine is used to drive the compressor. To optimize the transfer of kinetic energy from the combustion gases to shaft rotation, the turbine can have multiple compressor and turbine stages because the compressor must reach a certain speed before the combustion process is continuous or self-sustaining initial momentum is impacted to the turbine rotor from an external motor, static frequency converter, or the generator itself. The compressor must be smoothly accelerated and reach firing before fuel can be introduced and ignition can occur. Turbine speeds vary widely by manufacturer and design, ranging from 2000 rpm or revolution per minute to 10,000 rpm. Initial ignition occurs from one or more spark plugs depending on the combustion design. Once the turbine reaches self-sustaining speed above 50% of full speed, the power output is enough to drive the compressor. Combustion is continuous and the starter system can be disengaged. Case study: Kappa 180 MW power station. Kappa 180 MW combined cycle power plant project is one of the priority projects of Malaysia government. The main objective of the project is to compensate the power deficit of the country, particularly in central zone, and improve problem of low voltage in the said region, central Kappa and adjoining areas. The other aspect of the project are to cope with expanding power demand of the country, reduce transmission loss, and increase the stability of national grid system. The Kappa 180 MW combined cycle power plant is situated beside the grid substation at Jalan Tok Muda, Selangor. The data for this case study of this article has been collected from Kappa 180 MW power station. Data of monthly electricity generation for single cycle and combined cycle power plant are respectively shown in Table 1 and Table 2. From efficiency calculation of single and combined cycle, it is found that average efficiency of single cycle is about 25 to 35%, whereas the average efficiency of combined cycle is about 40 to 50%. Consuming the same amount of gas, the power generation from combined cycle is more than that of a single cycle. For Malaysia, natural gas reserve is getting lower day by day. Applying the combined cycle using the exhaust gases coming out from the single cycle, it would be possible to produce more electricity. This will minimize the cost as well as the gas consumption and will increase the power production. The conclusion: the simulation output show that if combined cycle power plant could be introduced in Malaysia, there would be huge rise in the power production. As the natural gas reserve is getting lower in this country, it will be more beneficial for us if we use combined cycle in power generation. The gas turbine power plants require availability of natural gas with proper pressure at all times. But in Malaysia, it is difficult to fulfill all these conditions at the same time. Through combined cycle, we can increase the efficiency by consuming the same amount of gas that we use in the single cycle and can produce more power, which can minimize our electricity scarcity problem up to a certain limit. Thank you very much.